Another concept that's related to net force and to three-body diagrams is something called equilibrant force. Equilibrant force, what it is it's the force that you'd have to put on an object that would exactly balance the existing net force on the object. Like, for example, our three objects, our snowmobile, pickup truck, and ATV, we found that their resultant force was this. It was a force of 18,429 newtons, and it was pulling at 3.2 degrees from where the pickup was towards where the ATV was. Well, what would we have to do to exactly balance that force? Well, the characteristics of equilibrant force is it has to have the same magnitude as the existing net force. If it didn't, one would pull harder than the other. So in our example, because we've got an 18,429 newton force, the equilibrant force would also have to be 18,429 newtons. But the other thing that would have to be true is the equilibrant force would have to be applied in exactly the opposite direction. So in our example, here's the equilibrant force on our three vehicles, 18,429 newtons, and it's at 3.2 degrees in this orientation. The equilibrant force would have to be the same magnitude, 18,429 newtons, and that angle there would also have to be 3.2 degrees. The equilibrant force placed on the exact same point of application as the existing force is going to cause it to reach equilibrium. Equilibrium means this. It means the net force is equal to zero. Now that might mean that nothing moves, but it could also mean that things move only but at a constant rate. Well, here's an example problem that involves equilibrant force. There are two dogs tugging on the same piece of meat. They're tugging at a 52-degree angle to each other. One dog can tug with a force of 85 newtons. The other can tug with a force of 105 newtons. And then the question is, how hard and in what direction would a third dog have to tug to provide the equilibrant force on the meat? Let's switch to another format and solve this problem. I'm going to start this out by modeling this problem using vectors. In other words, a free body diagram, like I always do. So here's my piece of meat. I'm going to model my piece of meat as just a speck here. And I'm going to first draw one of the vectors, and that's for the 105 Newton dog. And I'm going to kind of sketch him off this way. That's the 105 Newton dog, or the pull of the 105 Newton capable dog. So that's 105 newtons. The other dog is pulling 52 degrees away from this dog, and you might sketch it in any direction you want. They don't really tell, but we do know that they're 52 degrees from one another. And this dog can provide a force of 85 newtons. And our job is to figure out if there's a third dog, how hard would that dog have to pull and in what direction to balance these two out? That would be the equilibrant. Now to find the equilibrant, the first thing we've got to do is find out what the resultant is. And then just equal and opposite from the resultant would be the equilibrant force. I'm going to figure this out using the method of resolving vectors into components, which is my favorite method to solve these kinds of problems. So I'm going to create two axes. The first axis, which I'm going to call Y, goes vertical right through there. And the second axis is the one that lines up. It's going to line up exactly with this 105 Newton dog. And I'm going to call that X for lack of better terminology. So I want to have everything either lie on the X or the Y axis. Well, the 105 Newton dog vector already is on that axis, so that's easy. So we're going to have to split the 85 Newton dog force into two components. One component is going to go on the x-axis, and the other one goes on the y-axis, like that. And the sum of those would be the 85 Newton force. Well, what we've learned here is, by doing these kinds of problems, is that opposite the angle you have the sine times the hypotenuse. So the size of this vertical vector is going to be 85 newtons times the sine of 52 degrees, and adjacent to the angle you're going to have the hypotenuse, 85 newtons, times the cosine of 52 degrees. So let's figure out what these are. (85 sine 52 degrees) is 66.89, I'm going to say 67 newtons. 85 times the cosine of 52 degrees Comes out to 52.3. I'm going to say 52. So what does that mean? Well, if I take a look at the x and y components of my resultant, this is how I'd lay them out. On the x-axis, taking this as positive, this direction is positive, I have a 105 Newton force from the dog, the first dog, and from the second dog I have this 85 cosine 52, or this 52 Newton force. So all in all, that's 157 newtons on the x-axis, positive. On the y-axis, when taking the up direction as positive, what I've got here is just my 67 newtons. That's the component of the 85 newton in that direction. So the resultant vector I can find with Pythagorean theorem, because x and y are at right angles to each other. So this is 67 newtons, this is 157 newtons, and the resultant of these two vectors is the hypotenuse of that triangle. So that I can find by Pythagorean theorem. My resultant is 170.7. Now to find out the direction that these dogs are pulling together, I can find this angle using tangent. That angle theta is going to be the inverse tangent of opposite, which is 67 newtons, over adjacent, which is 157 newtons. Calculate that, and it comes out to be 23 degrees. So these dogs are together pulling with a force of 170.7 newtons at 23 degrees towards the 85 Newton dog from the other dog, from the 105 Newton dog. Alright, so what's the equilibrant? Well, it'd have to be just the opposite. 170.7 newtons this way at 23 degrees. The equilibrant is going to have to be 170.7 newtons at 23 degrees from this axis, or in other words, that whole angle away from that one dog, or 180 minus 23 away from the 105 Newton dog, would be another way to specify that orientation. So the equilibrant is equal and opposite.